Hi guys, so we can continue with our divide and conquer algorithms, but we're now going to pay attention to their complexity. But before I do this, I'm going to give you what's called the master theorem that will give us an insight in the complexity of these various divide and conquer algorithms. But I want to go back to one example that we discussed, and let me discuss it one more time, because it kind of illustrates a little bit everything that goes on. Remember the problem of fast multiplication. So fast multiplication, and this was of, of binary numbers, and what we had were two numbers. So we had the number A and B. This is doing A and B, and they were both of size 2n. They had 2n bits, let me put it that way. So of 2n bits, it's easier to take 2n here than instead of n. So, and then what we do is we divide their bits, so these are the bits here, I'm not going to write them, but they are ones and zeros, right? And divide them in two equal parts, and we call the first number A1 and the second number A0. So these are now size of, both have size n bits. So these are like 1, 0, 1, 0, 1, something, and here 0, 1, 1, 1, and something, 0 perhaps, okay? Something like that. And so A1 is now referring to this number if you ignore the last n, and A0 is the opposite. And the same for B. So again, we do the same here with B. We split it in two parts. So that is B1 and B0 here, both have then n bits. And then was this famous there was this formula here that was perhaps not obvious at all, but let's write it up again. 2n plus 2n. It's not hard to check that this is actually what things are equal to. n plus 1, and that's A0, B0. Okay. And what's the point now? The first observation is observe that addition has complexity n. If I have to add two numbers of n digits, then I do one digit at a time. Right, as we would, like if you would add these things here, you go, both have size 3 here, so you add the last digits, okay, that's a 0 with a carryover, then you add the next digit, that's a 1, and add the next one is a 1. And that's it, that's the only thing one needs to do, so we go through the whole, to both of them at the same time, and that gives me n. However, multiplication, we show that's different, so this is addition. If we multiply, okay, that's now not, that's a bit of a silly number that I took, I guess, right? So I should have perhaps taken this here. So let me take the number, that's twice the same number. Okay, it doesn't matter, that's twice the same term. Now we have to do this bit, the whole times the top number, then this bit times the top number. Well, of course it's 0, that makes it easy, but each time we have a 1, we have to do this. So we're going to do 3 times each time, and then also 3 times. So this size is n, and this size is n. So in total we do n square calculations. That's how it would be if I have to multiply two n-bit numbers. So of course we are actually multiplying two n-bit numbers. So in the complexity here, so this should be 2n, and therefore this would be 2n, so it should actually be 4n squared. Whereas if we have 2n here, suppose we adding these, 2n, we adding these, so the complexity of the addition, so this is multiplication, the complexity here would be 2n. But that's of course the same as on, and same for 4n squared, that would be on squared. So addition, if you just naively add, then it's on, and multiplication is naively n squared. And addition cannot be done better, but squaring can be done better, and that is because this formula gives us the following strategy. We divide the problem in half by looking at the AIs and BIs. Okay, look at what we need to do. We need to find A1, B1, A0, B0. Those two are okay. They are just by splitting here. That's just a simple operation, right? These two are subtraction that can be done in time n. We only need n calculations for that. Okay, so to get these numbers, that doesn't require that many steps. All right. Now the point is that we're gonna have, this is a number of n digits, this has n digits, so we multiply this, so we have reduced now our problem that was on 2n bit multiplication to a multiplication of n bits. And it's 3 times. We have it here, we have it here, and we have it here. So 3 times. So let's the complexity of this algorithm, the number of steps of 2n. If I start with 2n, it's easier to write it that way. Then I'm making it into a problem. I'm dividing into a problem of half the size. Now these are the capital A's and B's that are numbers of size n. The original ones were numbers of size 2n. Okay, so we reduced it to a problem of size n. And how many times do we have to carry out that problem? 1, 2, 3 times. Okay, now you might say, what about these factors here? Because there are also bits numbers that we have to multiply with, but multiplication with numbers of this thing, these are numbers with a lot of zeros in binary. This has 2 ones, this has only 1 1, and this has 2 ones. Those again need way less steps, right? We saw that here when we multiply with 0, we don't need to do that step. Now, in general, the number of ones and 0 are going to be kind of average the same, right? They're going to be almost as many ones as zeros, but these are special numbers. These are numbers with way many zeros and with only 2 ones. Each of these has at most 2 ones. So that multiplication with such numbers is extremely fast. It is these multiplications that we have to carry out 3 times with really numbers that could be of any numbers with any I have to use the word too. Numbers with any number of ones and zeros. Okay, so we have to do it 3 times, half the size. But then we have to put things together, and we have not specified exactly what is this. As I said, we have to do this kind of stuff, and then we have to also add them. And so there is some constant c. C is a constant here. So c is a constant. So this is the only kind of unknown in this thing that you can figure it out. If you really think about it, you can make this constant more precise. But you'll see that's the only thing I don't need to know. But what is important is the 3 here, and the halving. So let me make this clear that I actually am halving this. And then c times n, or c times 2n, because the original thing was in terms of 2n, right? So this was in terms of 2n, so I can write this in terms of 2n, so I could put a 2 here. After all, this c is a constant, so I can absorb that 1/2 into the constant. So in other words, if I replace 2n by m, I see that this is the form of my, so I'm using, instead of 2nm, to analyze it, it was even easier to think of n as an even number, but in general we don't need to do this. Although I explained it last time, when we calculate complexities, if we divide by 2, we assume that the size is a power of 2. If you divide by 3, then we assume that the size is a power of 3, so that keeping dividing by 3 in that case will never result in, we'll always have a whole number. That's just for simplicity, for making simple. You might say, yeah, but that's tricking things. Not really, because what I'm doing is, okay, suppose in this case I have to do this with digits of odd size. Well, just put an extra 0 in front of both of them, then they have even size, and you didn't change anything. You made it bigger, so to speak, but so now you have even size and you can work with the even size. Okay, so now remember we said that this was of multiplicity. Okay, that's now, instead of n's we are using m's now. It doesn't matter, right? There are variables. So addition is of complexity m, that's never going to change. Multiplication in the naive way in using our, let's say, first grade calculation method is of complexity m square. Is this better? Is what we do now. So f is here the complexity of this algorithm, and it satisfies this recurrence relation. So we would like to solve this recurrence relation. In fact, that is in general quite difficult to solve a recurrence relation like this. And in the book they gave very special cases, but not this one. The problem is that there is an m here. If this would be just a constant, then you could write down a solution. But we are not actually really interested in a solution. We are interested in the rate of growth. Okay, so this is the number step. What is the complexity? Okay, remember the number of steps, we kind of really count the number of steps, but when it comes to complexity, we do our big O estimate of that function. So how does that work? Okay, and here is what we call the master theorem. So I'm going to write it here and then, okay. So the master theorem. It's called like that because it kind of covers all possible cases. Well, first of all, how is a general case look like? A general case that we will be interested in is where the recurrence relation is of this form. And so we have three constants here, A, B, and D. What about C? We'll say, yes, it's also constant. So C is also constant. But as you see, this one will not affect anything. So if this is 5 or this is 70, it makes it perhaps slower and a little bit slower. But as far complexity is concerned, it is the same complexity. But A, B, and D all play a role, and rather subtly. So I'm going to have to explain this now. Notice that this B is the number of times that we divide the problem. Very often, in many cases, like in the binary case, we divide it into two, right? We divided everything in half. This was the half divisor. But if you remember, there's that in discrete math 1, in one of the homework problems, there was an algorithm called ternary search, where, remember, binary search, you would search in a list by cutting the list, an ordered list, by cutting the list halfway, and then search in one of them. And so, in other words, you would have reduced it to size half. But ternary search, you do actually smarter. You divide it in 3 equal parts, and you try to figure out in which of the 3 parts am I, and then you only work with that third part. So there you would divide by 3. I'll do that example in more detail, but just give you an idea that it doesn't always have to be 2. And so B is the number of times that we divide the problem in. Okay, that's the B. A is the number of times that we need to put it together. So here we see how many times that we, sorry, I'm saying it wrong, sorry. A, the little a here, sorry, A and B are not the same A and B as in this problem, in the calculation problem, right? Don't confuse them. These are A, B, and C that come from as they appear in this formula. We will look at concrete examples, but I first want to say, what is A represent? A represent how many times, so B represents, I'm going to divide the original problem in B equal parts, and how many times am I going to apply my algorithm to such smaller guy? A many times. And so here you see this, we divided everything in half, so B is 2 here. So let me write, okay, this is stupid that A is A and B and B here, right? So I'm going to make this A in a capital A and this in capital B, and so these are capital A and capital B. Okay, then we have no confusion. Okay, so in this problem, B was 2 because we divide in 2 here. That's the division in 2. Okay, now what is little a? How many times do we carry out the smaller algorithm? In other words, how many times are we multiplying numbers of bit size n? Well, as I said, 1, 2, 3 times. Remember, this is considered as one n-bit number, this is another n-bit number, and so it's the multiplication of those two that is where we do it once. We don't want to expand this, right? Because that would make it in 4. You want to keep it as one single. Think of this as a single n-bit number. This is an n-bit number, and we multiply them, so this is one instance of the smaller. This is another instance of a smaller, and this is a third instance of a smaller. So A is 3 here. Okay, and then we have this part where we put together. This is the divide part that we so far discussed, and this is the putting together part. In this time, it is a constant times m. We will look at other examples back and see that these things can happen. In fact, what only thing that we are interested in is the degree that we add here. And note that this can include that this is just, there is no m at all if this is just a constant, and that would be degree 0, right? Okay, so in this particular case that we have just analyzed, we see that d is 1, right? So I'll write it here one more. We can see it here, right? So the a is 3, the b is 2, and the d is 1. Okay, this was m's, but we kind of forgotten what these m's were, so I'm going to write n's again, right? And originally there was a reason why we did with n's and not with m's, but let's forget why we did that, and now we know that's how it looks like. So you see much better how it fits. Okay, now that's the setup. What's the master theorem say? Well, there are 3 cases that we have to look at. Okay, case 1. If A is less than b to the power d, weird, right? That this is a condition. Then the multiplicity is, the complexity is O n to the power d. Case 2. If A is equal to b to the d, then the complexity is n to the power d log n. We have to add an extra log here. And case 3, well, you can figure out what case 3 is if A is bigger than b to the power d, right? That's the only other option left. And so that is then O is, and this is perhaps the weirdest of all, n to the log with base b of A. Okay. Now, first remark you may say, oh professor, but I remember from last time when we do a big O, then doesn't matter which log you took. This is the log with base 2, I assume that you mean, right? But I didn't actually write it out, so it could be the natural log, or it could be the log with base 10. And you're right. The complexity of the log doesn't depend on the base. But this is not the log. This is a number that is calculated using a very specific logarithm, a certain base, right? So I'm not, the n lies, here's the n, and n is a certain power. So the complexity that I'm writing down is basically saying it's n to a certain power, and to calculate the power you need is log b. Okay, that's how it goes. So let's see where we are now. So I have A was 3, B was 2, and D was 1. So what we have to calculate is A, and we have to compare it with B to the power D. So A is 3, and B to the power D is 2 to the power 1 is 2. So in which case are we? And we see we are in case 3. A is bigger than B to the D. Okay, so the complexity of the fast multiplication has complexity O is n log B is 2, the log 2 of 3. You say, what is that? What are you doing there, Professor? Log 2 of 3, what does that mean? Well, that is about 1.6, so this is O n 1.6. This might be something you are not used to anymore, that powers do not need to be whole powers, right? We in calculus we have seen that you can take any type of power. It can be a fraction, or even more. This is a real number. Okay, I have it's log 2 of 3 is not equal to 1.6. It's almost equal to 1.6. So it's an estimate again. And in cases when we talk about big O, we should take the upper estimate. I'm not 100% sure whether it is the upper estimate, but that doesn't matter. What matters is this. Look, actual multiplication, the multiplicity, let's go back to our n's here. Straightforward multiplication using the usual technique of multiplication has complexity O n squared. Is this better? Yes, 1.6 is less than 2. So this is better than usual multiplication, because which has multiplicity, has complexity O n square. So we have done better. It doesn't seem a major improvement, but if you take n to be a million, then a million squared is way bigger than a million to the power 1.6. I don't know whether I'm sure million is perhaps a bit too big for my calculator to work with. I'm sure I'm going to do 1,000. The difference between 1,000 squared and 1,000 to the power. Let's see. Normally you need to take really higher powers here. Oh, I need to open this up in the, yeah. Okay, so we when doing 1,000 to the power x 1,000 1.6. It's about 63,000. So 1,000 to the power 1.6 is about 63,000. Now what is 1,000 to the power 2? That's a million. And I don't know about you, but if this is, we were talking about the prices or something like that, it's very clear that 63,000 is way smaller than a million. So although it looks negligible, 1.6, who cares? That's a power. You see, it's a major difference. Okay, so even these small improvements can make algorithms actually. Is the difference between workable and not workable. Okay, although if you remember from Discrete Math 1, we made a distinction between algorithms that were in polynomial time and algorithms that were in exponential time, and the ones in exponential times were considered insolvable, or rather could not be carried out with took too long to carry out, so and they were therefore very good for cryptography. So in this case we didn't change that. We in both cases, the original one was already of O n squared, so of polynomial complexity, and but the only thing we did was improve the degree. But as I said, this is now let's say a more refined study of these problems, and you see it has bearings in how efficient algorithms can be. Okay, so let's look at the other problems that we have been discussing, and perhaps why not look at ternary search? I did binary search, but since I mentioned it, let's do a ternary search. So go look up what it is. It's in one of the homework problems, but there's an index. You can look in the back at ternary search, and it will tell you on which page it is. So ternary search, we have a list. List is an ordered list, so a sorted list. And we have a smallest element A1 say and the biggest element AN, and we divide it in 3 equal parts. Okay, so we have an element here, we have an element here, and we have the element. And so the question is, where is X in the L? Where is a given element X in this list L? Is it in there? But more importantly, we assume it's in there. For instance, a name that we know is in this database. We just have to find the record number. So which position is it in? And what we did was we divided in 3 equal parts, and then we checked, is X bigger than this? Sorry, if this number, the last one in the first part, if X is bigger than that, we know it must be in the second. So let's call this part 1, part 2, and part 3. So if this checks out, then we know it's either in the second or third. If it doesn't check out, we know it's in the first. So now we also compare it with this, and we say, is X less than this thing here? So let me write it that way. So is X less than this guy? Whatever this guy is, right? We know it's a number somewhere in the list, or a word that we compare alphabetically. So if this checks out, then it's either in the first or the second, and if it doesn't, then it's in the third. And by these 2 tests, we know exactly in which part we are, and then we repeat our search with that part only. So let's now analyze what's the complexity of this. First of all, we divide here in 3. We divide the size in 3. So the B will be 3 here. How many times do we have to carry out the smaller one? Oh, only once. Remember, it's wherever it lands in, say X after we tested this X seems to be getting in part 3, then we will only carry out the search in part 3. We don't care about part 1 and 2 anymore. So we only have to carry it out once. So A will be 1 here, so I don't need to write it. And then you have to put things together, and in other words, that was basically these two comparisons that we have to carry out. And then also see, another thing that we need to do is, how does this stop when our list has been cut down to a single element, and then we know that if it's in there, it must be that element, and otherwise it's not. So that makes it a constant here. Okay, so you can, it's the same as binary search. We discussed binary search in the previous video, so just look at it. The only difference is that B is changed. Okay, so this was for ternary search. So let's look at where we are. So what is D here? This is a constant, so D is 0, right? Okay, so the question now is, we have to compare A, and this is perhaps weird, right? That it's these two combined as to be compared with that. It's weird that that's what it is, but that's why it's called a master theorem. You have to be a master to come up with something like that, right? So let's calculate these two numbers, A and B to the power D. So A is 1, and B to the power D, that is 3 to the power 0. Of course, that is just 1. We have equality here, so we have equal, so we are in case 2. And this tells me it is n to the log D, n to the power D, but D is 0, log n. So this is a search of complexity. F of n is complexity log of n. Now this is very important. This is a search algorithm that has log n. And if you think of linear search, what would this linear search do? Linear search was just look at the first element. Is this it? No. Go to the second. Is this it? No. And you keep going. And worst case scenario, you have to go all the way to almost to the end before you actually find a match. If at all you find a match. So the complexity of that, if the linear search, so the complexity of linear search, let me write it this way, complexity of linear search, and this is something that was already discussed in discrete math, 1 is O n. So we improved. Okay, so that's very important to notice. But let's now, and much more important actually is this. This linear search is kind of cheating in the sense that I am using a sorted list, and linear search doesn't. So I cannot apply this on I have to first sort my list. So the more pertinent question is, what about sorting? Okay, so we discussed sorting. We saw these are again examples of divide and conquer. The merge, when we talked about the merge sort, the other sort, bubble sort and insert sort and whatever sort we saw before, those were not. But I remind you of the merge sort again. Let me one more time give an example. Suppose we do, I go and do it with letters. It's a little bit easier to see what is going on. C, B, R, O, D, say, okay? I take here again 8 because it's a, what are we going to do? Divide in 2. So we know that B is going to be 2, okay? And then we're going to sort each of these separately. So this tells me already what A is. A is going to be 2 as well, because I'm going to sort this one, I'm going to sort this one, and then we have to put them together. And so that part, so where are we now? The complexity of merge sort, or the number of steps that you need to do in merge sort, f of n, is 2, f, n over 2. And how do you put it together? And we discussed this last time, what you need to do. So remember, I apply now the same algorithm to KMAC, and then inside the box, let's not look inside the box, and as the result we know we get of course ACKM, and not looking what happens here, just skipping all the steps. We know now this is the number of steps we need, that's why we don't need to write it down anymore. If this is being ordered, that would be B, D, O, R. But then we had to put this together, and how did we do this? We would go through each of these lists. We would look at the first element of this list and the first element of this list, and we would take the one that is smallest, and we put that first. And then we would erase that from that list and look at the next element and compare again. So we compare these two, and this is B. So again, now B goes. So now we have a new one, so we're going to compare these two, and then C goes. But and so on. So what happens is what it means is we're gonna have to look at each of these elements once. Okay, every element will be chosen at one stage or another, and exactly that. Nothing else happens. So this will be n more steps plus n to put it all together. Okay, so B is 2, A is 2, D is 1. So again, we have to look at A and B to the D. A is 2, B to the D is 2 to the power 1, which is 2. We are again in the middle part of our case 2 here, and so we have this is O n to the power 1 log n. So the multiplicity f of n is O n log n. Now this is very important because the bubble sort as well as the other sorts that were discussed in insertion sort and perhaps even other sorts that were discussed in the homework in discrete math 1 all were of complexity O(n) squared. So let me perhaps record that. Bubble sort as complexity n squared. Basically what we had to do is we look at each single element and see whether it sinks down or not. And if it's and at the end we will have after the first pass through the whole list, the biggest element will be in the end. But then we have to repeat this for the next biggest element. So we had to go through this list n passes, and each pass was n steps or thereabout, and therefore the multiplicity was O(n) squared. Again, this is analysis we made already in discrete math 1. If you don't remember this anymore, go look it up in that chapter. This is better. It doesn't seem majorly better, but it is better. And again, just to convince you what it is for 1,000, let me see whether I can do this. 1,000 times the log 2 of 1,000. No, that doesn't work. Sorry. No, that's log 2, that number. Okay, I found it. So the log 2 of 1,000 is about 10. So this would be if n is 1,000, this number is about 10,000, where this number of course is 1,000,000 again. And you see major drastic difference. And after this becomes even more dramatic if you talk about millions and so on. Okay, so that's examples of how this divide and conquer work. Let me see. If an example, I kind of need not remember anymore. No, I don't have this. Sorry, I'm looking. I'm sorry, give me a sec. I'm looking for a problem. Where was this? Oh, yeah, right. This is the one I want to do. Now, fast matrix multiplication. Now, I know that not all of you know exactly what matrices are. Last time I kind of explained it a little bit. And so we have a matrix of size n by n. The size is n, so size is n. So there's n square elements. So it's a table with n square elements. Okay, so there are n rows and n columns, n rows and n columns, table of this many elements, and we multiply them, and we had to calculate n square elements, and each calculation involved n steps. So altogether, regular matrix multiplication is O(n) cubed, as you learn it in linear algebra. It's n cube elements. Now, there was this algorithm devised quite recently. People have worked at this and they found a better one, and I don't know how it works. It's rather complicated. But what you do is, again, you make matrices of half the size. But strangely enough, in this thing you need 7 matrices of half the size. So you're going to apply this same algorithm two matrices of half the size, but it's not just one, not two, but 7. Okay, we have seen now that this can happen. So I remind you, you might think, oh, I divided half, then therefore I have to do it twice. No, that's not necessarily the case. I remind you here, we divided the problem in half, but we needed to do it 3 times. Okay, so these things are really not, they look connected, but they are not. So that's it. And then the putting together took also a little bit of time. It was n squared over 4, the actual constant. But again, the only thing that doesn't matter is this number here. That's the C here. So what we have, A is 7, B is 2, and D is, it's the degree, 2, that matters. Okay, so we have to compare A with B to the power D. A is 7, B to the power D is 2 to the power 2, that is 4. So A is bigger. So we are in this situation again. So it is this rather strange number, O of n log B of A. Log 2 of 7. Now, log 2 of 7 is almost, it's written down somewhere log 2 of 7 is about 2.8. So log 2 of 7 is about 2.8. So this is O n 2.8. So is this better? Well, I said it was O n cube. It was polynomial, but we can do a little bit better. And I hope by now you're convinced that even on big sizes, this makes really a difference. I'm not going to work it out here because these are already getting big numbers, right? Even with 1,000 to the power 3, that is a billion. So, okay, and so suppose just for the heck of it, because we haven't really seen a case like that. That's what I'm looking for, and for some reason I cannot find it. Give me a sec here. Yeah, so imagine, let's just write down an example. Suppose that f of n is equal to 5fn divided by 4 plus cn square. Let's try, what's the complexity of f? So far I've been analyzing particular algorithms and the number of steps that we need, but this is a more general theorem. It says this theorem is not just about certain algorithms, this theorem is of any function that is given by a recursion formula of this type, which is called a conquer and divide recursion relation, has this complexity, which depending on the case that we are in. So analyze again, what is A here? Well, 5. B is 4. Now we don't think of this anymore as an algorithm. We just think, what are the numbers? What are the parameters here? So A is the number in front, is 5. The number that we divide by is 4. And then C, the constant doesn't matter. What matters is the degree, which is 2. And so we have to compare A with B to the power D. A is 5, B to the power D is 4 squared, that is 16. So we are less here. So we are in the very first case, and the complexity is therefore O n squared. This D here. Okay, and that's it. So we have seen now a little bit of everything. I want to mention one thing. I invite you to look at the explanation. It's quite lengthy. There's a problem, but it's a very important problem also, is you have a bunch of points, let's say spread out, that's cities, say, and suppose you are a trucking company and you say, okay, we're going to start small, guys, and we're going to have a truck run from one city to another, and I'm going to pick the 2 cities that are closest to each other. Now, of course, we, on a small sample, and then you see that this is the closest pair. So this is the closest pair problem. But imagine, just a map of the US where we look at all the cities of size at least 100,000. And then you get a lot of dots all over the place. Of course, in our area here, there's going to be quite a lot. We have New Jersey, we have Jersey City, we have Newark, we have Patterson. I'm not sure that Patterson has 100,000, but it's near there. New York City, of course, is there. We have upstate, White Plains, and so these are big cities all, and so we have a lot of a cluster there. But if you go in Midwest, the clusters will be much smaller. And say, okay, in Ohio, I want to find the two cities of size at least 100,000 inhabitants that are closer to each other. And if you have a big sample, you cannot see it anymore. So you have to do this. And how would you naively do this? If you cannot look at things, if you just have to do it, well, what would you do? I take this point and I compare the distances. And whenever I find I start with the first point and I compare it with the second point. I call that, and then this distance is my smallest distance. Compared to the next one. If this distance is smaller than the previous one, I'm gonna change my mind and say, okay, this becomes the new smallest distance. And I do then this, and I do this, and this, until I convince myself the smallest distance of this point to all points would be this one. But is this now the smallest distance in total? No, of course not, because now I've looked at the second point and start comparing it with everything else, until I find something that is smaller in distance. Perhaps this doesn't happen, but once I'm taking these points, we'll find things closer by. Meaning what? I have to go to each of these points, which is n of them. So again, we have closest pair among n points. I'm going to look at each point and compare it with all the other n points, or n minus 1 points. And I do this for each n separately, just the naive search. So the naive search, you can write down a program for that, would be O(n) square. Okay, so in the book, the quite lengthy explanation here is you find an algorithm that is, the number of steps is, you divide the problem into again, and what you basically do is you divide basically in two parts, and you look at the closest point here, the closest point there, and then you have to still compare whatever is in the boundary kind of if there are no better solutions that come from one point on the left and one point on the right. So, and that you have to analyze that as well. And so it turns out, since we have to look at the left hand side and find the closest pair there, the closest pair on the right hand side, so we have to do it twice. And then we have to also look at the boundary here, which is a small strip. We have to see whether there are any better solutions there. So remember, so for instance, what could have happened is this, right? So let me get rid of a bit of this. I could have divided my sorry, that's not what I meant to do. I could have divided my points here. These are the points, but I could have just split the actually smallest of all combinations. And so if I would do it that way, the smallest distance that I would find is perhaps, let's make it this here. I would say that this pair, and here the smallest was perhaps this one. So is any of these the smallest? No, because there's actually a crossover here. But this crossover cannot be in a big region. It must be a region smaller of this size. So you just have to compare much fewer elements, and this is what accounts for this 7n here. Anyways, that is very quickly saying what is a lengthy calculation in the book, which I invite you to read. But this is the complexity of this algorithm, and now we want to know, is this better than this n squared, the naive search? Okay, so A is 2, B is 2, D is 1. So we have A, and we have B to the D. A is 2, 2 to the power 1 is 2, so we are in the middle case. So we know that the complexity is, yeah, this is something you want to memorize perhaps even, but of course it's open book, so you don't really need to do it. It's given by this formula, right? So n to the power 1 times log n. So O of n log n. But this is that's the whole key here. N log n is again much better than O n squared. So this was O n squared when we just the naive. This was the naive algorithm, right? Okay, I hope I convinced you that this divide and conquer is already kind of subtle, and it's first of all not obvious to come up with these kind of algorithms that are smarter somehow, but they're not just smarter, they actually are better. And of all what we discussed, really important is the fact that I guess I have erased it, that the merge sort has sorting n log n, which is faster than n square, and at the moment it is one of our best sorting algorithms. And it is a little bit counterintuitive, right? It looks like it's a lot of steps. If you remember from our discussion, we have to keep breaking it down and then we have to putting it together. Seems like you have to do a lot, but in fact it actually is not. It's only n log n is as opposed to n square. And so once we have that the merge sort, this is O of, lost my pen somehow, I don't know what happened. So the merge sort was O n square. Now remember that the ternary search, if we do the ternary search, I don't know, ternary search, no, it doesn't work here. I don't know what my pen is. Okay, let me get out and in again. Okay. Yeah, my pen has given up. I don't know why. Okay. Anyways, one last thing I want to say. Ternary search was we figured out was log n, right? You see it here down here, log n. Ternary search assumed that you had to sort your list, so you had to first sort it, and that was n log n. So this is really search is therefore perhaps is that it's not yet the best solution, because linear search was just n steps when the list was not ordered. So here sorting cost more, but imagine this: if you have to keep searching for something, not once but 100 times or even n times, like Googling something, you each time are consulting the same database over and over, then true, linear search only needs a complexity n. So if you don't bother sorting your list, you can do it in n times, but if you have to do it too many times, let's say n times as well, then becomes n squared problem. Whereas if you would sort your list, then it's n log n, and then you would only have to do log n searches. Okay? And so even if you have to do n searches, each takes log n of time, the sorting itself also takes n log n, so the whole thing can be done in n log n. So it's sometimes, it's not just, an algorithm doesn't stand on its own, right? It's very often you use an algorithm many times, and that's why we want to get very fast algorithms, even if they require extra steps, like sorting first. Okay, I'm going to stop here. I'm going to assign some of the homework problems. Mostly we'll be applying the master theorem to particular examples. The analysis of algorithms and so we have done in the part 1. So there will be not, I don't think, perhaps one homework problem asks you to set up a similar kind of divide and conquer algorithm, but most of it will be about the functions.